As you all know, a major earthquake is usually followed by a number of aftershocks, and those aftershocks in themselves can not only disrupt response and recovery activities, but can also be very damaging and deadly themselves. And a particular example of a damaging, deadly aftershock was the earthquake that occurred in Christchurch, New Zealand, which was actually the aftershock of a larger earthquake that had occurred a few months before, but ended up being significantly more damaging and deadly than the main shock because it was located close to the city of Christchurch. Another example of an aftershock that ended up being more damaging and deadly than its main shock was the recent magnitude 7 earthquake in Japan, which was actually an aftershock of a magnitude 6.2 earthquake that had occurred the day before. And after we know this happens, we're going to rename that the foreshock and the main shock. But at the time the magnitude 6.2 earthquake happened, we would have been asking ourselves, what sort of aftershocks could happen? Could a large damaging aftershock happen? And we would be thinking about whether or not an even larger event than a magnitude 6.2 could happen, which indeed it did. So we do know quite a bit about aftershocks simply from having experienced a lot of aftershock sequences. So we can use our experience from past aftershock sequences to get an idea of what's going to happen in future aftershock sequences. So when an earthquake happens, we can make forecasts of how many aftershocks we're likely to see and what the magnitudes of these aftershocks are likely to be and when they're likely to occur. So, for instance, we can answer the question, how many aftershocks are we expecting? And that depends on the magnitude of the main shock. And so this is just a little table of what we would expect in terms of the number of aftershocks for an earthquake in California. And you can see that as the magnitude of the main shock goes up 1 magnitude unit, you get 10 times as many aftershocks. We can also say something about the sizes of the aftershocks that we're likely to get. And this is a table now of the aftershock magnitude and how many aftershocks of that magnitude we're likely to experience. Both the observed number we saw in the Northridge earthquake and the expected number just from our statistics. And again, you can see that there's a pretty easy relationship that as the magnitude of the aftershock goes down 1 magnitude unit, you get 10 times as many of those aftershocks. We can also say something about the timing of aftershocks. And this is a graph now of the aftershocks of the Northridge earthquake, the x-axis being the days since the Northridge main shock, and the y-axis just showing the magnitude of the earthquake. So each earthquake is shown as a circle on this plot. And you can see that the number of earthquakes decay through time, and you can see that just because the dots on this plot are getting sparser and sparser as you're moving to the right through time. We can also take a bit of a broader view on the aftershock sequence and look at a full year. And if you look at that plot, you can also see that the earthquakes are getting sparser and sparser through time. So this aftershock sequence is still going on and still decreasing in rate with time. And even if you look out a full decade, you can see this aftershock sequence continuing to decay for a number of years. So this is a reminder that aftershock sequences actually last a pretty long time. They're not just something that happen within the first few days of an earthquake. And that's something that we need to think about when we're thinking about any sort of response and recovery activity following a main shock. We need to be thinking about the possibility of aftershocks. So this is looking at kind of the stages of response and recovery in 5 stages and sort of assigning a little bit arbitrary but representative time period to each of those stages, and then looking at how likely are you to have a damaging aftershock during that time period. So this is a forecast as if we had just had a magnitude 7 main shock, and what's the probability of having a magnitude 6 or larger aftershock? So that's still quite a large aftershock. So that's basically the probability of having a Christchurch, New Zealand size aftershock. So during the emergency response phase lasting for a few weeks, there's a pretty high chance of a large aftershock, a 61% chance. When then moving into a restoration phase, say for another year, there's still a pretty high chance of a large destructive aftershock, a 33% chance in this model. And even when we're looking to much longer term activities, when we're looking to reconstruction lasting a few years, when we're looking at kind of a period of kind of betterment and getting ourselves ready for the next earthquake over the next, say, decade, And even when we're looking at very long term, what's our new normal, what are things going to look like over, the time period of the next National Seismic Hazard Map or something, even over those very long time periods, you still have this approximately 10% chance of seeing a large destructive aftershock. So we do need to be thinking about aftershocks for all of our planning in terms of response and recovery. So we've talked to different groups that use aftershock forecasts or that could potentially use aftershock forecasts to increase their safety and resiliency. And we've talked to a very wide range of groups, and this is a very short table just going over some of those groups. But if you're interested in reading more about what we're doing, there's a report that was recently published in Seismological Research Letters. So user groups range anything from the public, who can use aftershock forecasts just sort of as a reminder that aftershocks are going to happen, to remind them to prepare, to reassure them that the aftershocks they're feeling are normal and that scientists kind of understand what's going on with the aftershocks and they don't need to be unduly concerned that something unusual is going on. And also for the public to make some decisions that they need to make, for instance, about whether or not they're going to enter and use buildings that they might feel are vulnerable. Aftershock forecasts are useful for official advisory councils that are giving timely and consistent information to government agencies. It's also, we've spoken to a number of different emergency managers, both government and private sector, that see a lot of potential uses for aftershock forecasts, ranging from increasing their readiness to helping them decide things like beginning and ending evacuations of particular areas, locating shelters, planning supply routes, and other things like that. There's applications for the built environment. Particularly after a large event, there's going to be building inspectors and repair workers out there in buildings, and having information about aftershock hazards can help make decisions to keep those people safer. There's also the possibility of reducing repetitive repairs from repeat damage, and there's even the possibility of changing long-term zoning and building code changes, which is in fact what happened in Christchurch. We could see, for instance, in areas of induced seismicity, this could help oil and gas regulation think about decisions to make when there's a high probability of aftershocks. And finally, the insurance and financial sectors can think about things like increasing or decreasing reinsurance and buying and selling catastrophe bonds and other activities. So there's a lot of potential uses for aftershock forecasts. So currently the USGS does issue aftershock advisories following all magnitude 5 and greater main shocks in California, and we've actually been doing this for 25 years. This is an example of what we produced after the Napa earthquake. We have a forecast for the next week of how many magnitude 5 and larger, that is potentially damaging earthquakes, are likely to happen. A probability that we could end up with an earthquake larger than the main shock. So the probability that the earthquake we just occurred is just a foreshock. And also the expected number of magnitude 3 to 5 earthquakes that people are going to feel. And then there's also a little bit of text with background information about aftershocks. So as I said, we've been doing this for about 25 years in California. In the next year or so, we're planning to expand this to the entire US. We're also planning to expand the forecast to be over a range of time frames, not just a 1 week forecast, but forecast time frames from days to years. Because, of course, we do have to be thinking about aftershocks on all of those time frames. And we're also moving towards a sort of a more detailed advisory format than what I just showed, to have a text advisory that's sort of geared towards the general public to understand what's going on and to give them some basic information about what to expect, and also providing more quantitative information for the more technical users in the emergency management and financial and other kind of technical communities. So we would be presenting information kind of like this, for the example of after the Northridge earthquake. Instead of just giving you a few numbers for what would happen in the next week, we have time periods ranging from a day to a year and a number of different minimum magnitudes, giving you the expected number of events and the probability of occurrence. So that's what we're expecting to kind of have available in the next year or so. We're going to have some more things coming down the pipe that are going to be ready in the next 3 to 5 years, and Nicholas will be showing some of those plans in the next presentation. And sort of beyond that, we really want to work with users and potential users of Aftershock forecasts so that we can better supply them with the most useful information to them. So there are a number of different kinds of information we could be supplying about aftershocks. The first one is just the aftershock probability, which is what we're already supplying and are planning to, as I said, expand to the whole US very soon. We can also produce scenario aftershock sequences, just sort of different scenarios of how an aftershock sequence could play out with the relative likelihood of the different sorts of sequences. And again, this is something that we've seen very useful after the Christchurch earthquake. We could take this also to ground motion and give you the probability of an aftershock exceeding some level of ground motion at a particular site or a set of sites. We could take this also to ground deformation to look for the probability of liquefaction or fault offset or landslide at particular points. And we could take all of this and take it all the way through to a forecast of damage and casualties. The only caveat being is kind of as you're moving down this list, each of those things build on each other and build on kind of other parts, other pieces of information we would need to gather. And so these sort of forecasts would get more and more uncertain as we go down this list. But in any case, we'd really like to hear from you if you think you and your organization are potential users of Aftershock forecasts. We'd really be interested in hearing what kind of information you would want, what kind of time frames, and how you would like that delivered, so we can start developing kind of the next generation of products after what Nicholas is going to be talking about today. So with that, I'm going to turn this over to Nicholas to talk about some of our longer-term plans.
Okay, yeah, so like Jean said, what I'm going to be presenting here is some of our plans for what's in development over the next 3 to 5 years. So this is the sort of stuff that we might be implementing or talking about implementing at the next one of these meetings. And so again, the reason to introduce you to it here is so that we can start this conversation about what kind of information you can use and how we can best deliver it. Okay, so Jean already made this point here about the aftershocks having their own hazard, being potentially damaging, so I don't need to go over it here, except to point out that there are these other additional recent examples, in particular the Nepal quake I'm going to be talking about a little bit later. So this was a case where we had a magnitude 7.8 main shock. That was followed by a magnitude 7.3 aftershock that, although smaller than the main shock and less devastating, it still added a significant toll to the consequences of this earthquake. And then this case in Japan with the magnitude 7, where you had an aftershock that was even larger than the main shock. So one question, of course, is can we forecast these really bad aftershocks? So in the case where you had that aftershock larger than the main shock, as Jean pointed out, the probabilities that you get here are going to be fairly low, less than 10% generally. And that's because of the way that we generate these forecasts. Since forecasts generated in this way, these aren't predictions based on precursors, these are forecasts based on past behavior. So if you're using past behavior to predict what's going to happen in the future, if you have a rare event in the past, it's always going to be given a low probability in the forecast, just by definition. So with these really large aftershocks, we know, of course, that these low probability events happen with certainty given enough opportunities. So what we want to do is give you information that you can use to prepare and be ready to respond to these large, rare aftershocks as rapidly as possible. So in some sense, think about these aftershock forecasts as a shake map, something you're not going to use it to evacuate a city, but you're going to use it to best prioritize your resources when you're already going to be putting out maximal effort, and these tools will help you prioritize that effort. So there are a couple of steps that I think we can take to improve our ability to prepare and respond. I'm sorry about these titles there. Spilling over here. And this is epidemic type aftershock forecasting. So I'll introduce you to epidemic type aftershock forecasts, and then including a spatial component to the aftershock hazard. And I think giving aftershock hazard maps has a real potential to improve the usability of these forecasts. So let's start with epidemic type aftershock forecasting. In an epidemic type forecast, all earthquakes, even aftershocks, temporarily raise the probability of future aftershocks. So as Gene pointed out, all earthquakes of all sizes cause aftershocks proportional to their size. This is true for aftershocks as well. So you can think this is a model borrowed from epidemiology. You can think of the main shock here as a fault that infects the neighboring faults and sets off aftershocks. These guys are then carriers, and they can set off secondary aftershocks and so on. And in cases like some of the examples where you had large aftershocks, these are like outbreaks in the epidemic. So secondary aftershocks can set off tertiary aftershocks and essentially reset that aftershock sequence. So you might be in the middle of the aftershock sequence, you know the aftershocks are dropping off with time, but that's just on average. If you do have a large aftershock, that rate can get kicked back up to what it was just after the main shock. So you might not be able to predict these large aftershocks, but you can at least be ready to respond as soon as possible. And in particular, you want an aftershock forecast that can respond to large aftershocks that it's forecasting and be immediately updated, because you don't want your forecast to be invalidated by the occurrence of one of these large aftershocks that you're actually expecting. So, and this cascade goes on and on until no new faults are infected and the sequence dies out, so to speak. And this secondary triggering, of course, the main shock is usually the most important agent in setting off aftershocks. But as time progresses in that aftershock sequence, this secondary effect, the aftershocks of aftershocks, become increasingly important as sort of the memory of the original earthquake fades away. So the idea is by looking at the aftershocks themselves in the same way that you look at main shocks, you get increasingly precise information as that sequence progresses. And about 20% of aftershocks worldwide are secondary or later generations. In especially earthquake-friendly places like California, they can be 50% or more of the sequence. So there's a lot of information there that you can take advantage of. And this may seem a lot more complicated, but it's really just that basic Omori's law applied to all the earthquakes. And we've known this is the way to think about these sequences for 30 years. It's just that now we have the computational resources to be able to issue forecasts that take into account these effects. So this is an example. We're just starting to put this into use. This is the one case that the USGS actually issued a forecast based on this epidemic type model. And this was for that Nepal earthquake. And I can walk you through the slide a little bit here. It's the rate of earthquakes over on the vertical axis, the time since the main shock on the horizontal. You can see the rate decays. So that's kind of the standard Omori law representation. But if you notice, the difference with the epidemic model is you have these spikes in rate at the time of large aftershocks. So if you recall Tom Jordan talking about how the hazard from earthquakes varies in time, the hazard from aftershocks even varies within an aftershock sequence. So the hazard isn't uniform over that sequence. There are particular periods when you need to be especially concerned. So if you see, this is the magnitude 7.3 aftershock that occurred about 15 days after the main shock. It kicked that aftershock rate up to almost what it was just a few minutes after the main shock. So the epidemic type forecast immediately adjusts to these later aftershocks and takes into account the sudden increase in hazard. So what does the epidemic type forecast mean for you? You don't need to know the details of the model, of course. We'll just give you the numbers. But you might use this type of forecast in a slightly different way because it is going to evolve in time. So the biggest change is that we're talking about giving a live update, a sort of living update that takes into account up-to-the-minute information about what's happened in that sequence. So this is taking into account just not just how many earthquakes or aftershocks there have been so far, but how big those aftershocks have been and how that changes the hazard as we go along. So the one change is that it's going to be a time-varying forecast. It's more accurate, but it's also going to include greater uncertainty. Once you start, so the existing way that we forecast the aftershocks takes into account variability between main shocks, but it doesn't take into account how those large aftershocks are going to change the rate. So when you take that into account, it does raise the uncertainty. We'll be issuing larger upper bounds in general. So it sounds like bad news because if the range of numbers we're giving you is even larger, that's even harder to work with. But it has the trade-off of accurately capturing the variability in these sequences and what can actually happen. Okay, so that gets us to the goal of having fewer surprises. So we don't want to be surprised by these earthquakes. The step number 2, so the reason we need to go to the epidemic type forecast is because this is going to enable us to produce spatial maps of aftershock forecasts or aftershock hazard, which is what I think is really going to be useful. So I think some of you are familiar with Omori's law for earthquake distribution in time. Earthquakes happen close to the main shock and then fall off in time. Well, there's also an Omori's law for the aftershock location. They tend to happen close to the main shock and then decay away in space. So we can use that information. There's just some data showing that statistical pattern. Just need to know that they happen close to the main shock. Larger main shocks affect a larger area. You can plug this into your aftershock forecast. And secondary aftershocks happen near their own parents. So this is where the epidemic type forecast really comes in useful. So as an example, here's that Nepal earthquake again. These lines here are showing you the contours of hazard or aftershock hazard due to this magnitude 7.8 main shock represented by this big oval here. These small circles are early aftershocks. So this is a forecast that was generated 1 day after the main shock. You can see already that the main shock itself, the contours are smooth related to that main shock. All these irregularities are due to the effect of that secondary aftershock triggering. So notice down here where you see this little cluster. So this is a forecast 14 days after the main shock. You can see that the contours have all gone down a little bit, and it's also starting to get patchier in the interior where those early aftershocks are. So at this point, you can start to identify aftershock hotspots that are going to give you information about where to expend your resources. And in not all cases are going to be this sort of clear cut, but if you notice this hotspot over here where the hazard is kind of bulging out to the right, that's actually the location of that later magnitude 7.3 aftershock that was so damaging. So there's the hope that by mapping out the spatial distribution of the hazard, you can identify these hotspots. And then the other thing to notice is that now that this aftershock has occurred, even though it's smaller than the main shock, this forecast is generated 30 days after the main shock. You can see that 1 month out, that large aftershock is contributing more to the hazard than that original main shock. So this is why we need to go to this epidemic type forecast. And then a forecast a year later, so this was done pretty recently, you can see that the hazard is still elevated, but there's a spatial component to that hazard. So our hope is that you can use maps like this later down the road to prioritize the planning, preparation, retrofitting that you're doing or should be doing 1 year out from the main shock. Okay, to summarize, what's in the pipeline? The first thing is epidemic type forecasts that anticipate aftershocks of aftershocks and then use the aftershocks that have occurred to fine-tune that forecast as you keep going. So it's going to be more accurate, fewer surprises, but it'll require you guys to check in with the forecast because it's going to be more like a weather forecast where it changes with time as we get new information. And then the second thing is an aftershock hazard map, which hopefully will provide for rapid assessment of hazard and the identification of aftershock hotspots. So that's all I have. The question I want to put out there for you guys is, can you use, would you use, how would you use a forecast that evolved in time, where the information was continuously changing? How would you take advantage of that? And then would you be able to use spatial maps? How would you use that in your operations if you had something like this product here? Thanks.